big cooling effect. Volcanoes put particles in the stratosphere that reflect sunlight and cool the planet. And so these curves are all relative to a zero long-term mean. And then there are two man-made effects, greenhouse gases and sulfate aerosols, which are a form of air pollution that occurs when you burn fossil fuels or you burn trees to clear land. And that's a cooling effect. So when you look at all this together, you get a complicated picture. This warming in the early 20th century was mostly due to a combination of sunlight, a little bit of greenhouse gases, and a statistical absence of large volcanic eruptions from about 1980 to 18 to about 1960. Then this leveling off is mostly due to sulfate aerosols, countering some of these other effects. And then the rapid warming of the last 3 or 4 years is mostly attributable to greenhouse gas. Now, of these things, the sulfates are kind of interesting because they're unlike the other effects. Their sources of this kind of pollution are industrial, mostly industrial, and therefore mostly in the northern hemisphere. Sulfate aerosols have a lifetime in the atmosphere of about 2 weeks. So their concentration is very much determined by where the sources are. So the sulfates are mostly in the northern hemisphere. And this would be important in trying to reconcile the difference between the globe and the northern hemisphere. So what we see on this graph, going back to 1880, is the global mean surface temperature in red. The temperature of the tropical Atlantic in blue, which we've seen is highly correlated with hurricanes, and which is also highly correlated with the northern hemisphere temperature. And then this curve that starts at 0 and goes down is a measure of the sulfate aerosol forcing. It's an anthropogenic effect. And Mike Mann and I simply asked the question, can you explain the difference between the globe and the northern hemisphere by the fact that most of the sulfates are the northern hemisphere? Can you add this aqua curve to the red curve and get the blue curve? The answer is yes, you can. Yes.
Sulfates are a cooling effect?
Yes, they're a cooling effect. Right. And so you get this a very nice match when you add the global surface temperature to the aerosol forcing and compare it to the Atlantic tropical temperature. So this gigantic seesaw, which some folks have described as a multi-decadal oscillation, but I don't know of any statistician that would conclude that there's a periodic oscillation having observed 2 peaks in one trough in a time series. Doesn't stop geophysicists from doing but we don't think there's anything oscillatory about it, actually. It's just a coincidence about how the radiative forcing evolved in the 20th century. So in a nutshell, this ramp up here was partially solar, a little bit of greenhouse gases, and partially an absence of large volcanic eruptions, which are another natural cooling device. This is mostly man-made with sulfate aerosol cooling, particularly in the Atlantic. It's very strong because of North America. And then this ramp up is partially greenhouse gases and partially the fact that we've cleaned up our act. Right? We had a Clean Air Act and things like that. Cleaned up the atmosphere, at least caused the sulfate aerosol forcing to level off, if not decline. So it's a little bit of an irony. This silver cloud of the Clean Air Act had a black lining as it brought back intense hurricanes. Okay. You look all right. So that's about as much as we know empirically. Now, one of the greatest enigmas that remain in the field of tropical meteorology is called the Genesis puzzle. It's the whole idea of what controls the rate of tropical cyclone activity on our planet. Now, let me just show you what that rate is. This is simply the global number of tropical cyclones. It has nothing to do with their intensity from 1980 to 2010. Now, why this period of time? Well, we've had really good satellite coverage of the globe since the 1970s. We can count storms. We don't know how intense they are, but we can count them. And what you see is an average of about 80 or so, with a standard deviation of 9, something like that. Yes.
So, to be declared tropical storm, there's no specific, to be 39 miles an hour?
Yes.
So you have to have some intensity information.
There is. There is. It's mostly done by pattern matching. It's really primitive. You have a template of storms that you actually did measure, this is what it looks like on satellite pictures. Now you have another, I mean, it's really quite crude. You're right, you have to have a little bit of intensity information, but it's, I don't think, you know, if you played with that criterion, it would change this very much. I mean, it would probably just be an offset.
There's not a lot of storms right at